Today with a little demonstration. Now I have here a hammer, a soda can, and a brick. I'm going to go ahead and zoom the camera in so that you can take a look at what we're doing here. Alright, if I stack the brick on top of the can, are you able to see that?
Yes.
Alright, I'm going to take the hammer and I'm going to pound it on the brick. Team Alpha, what do you think is going to happen to the can?
The can will be crushed.
The can will crush. It sounds like a genius idea to me. Let's try it. Here we go. Uh-oh. Did it crush all the way?
No.
Let me try it again. All right, I'm not having a bunch of success. Let's try this. I'm going to remove the brick. I'm going to hit the can with the same amount of force. Team Bravo, what do you think will happen now? Let's try it. Okay, 2 hits of the hammer now easily crushed that can. Now let's talk about why that's the case. Why did it not crush the first time? Team Charlie, why do you think it didn't get crushed to this extent the first time?
After blocking it.
I like how you worded that. The brick blocked it. The brick, was it at rest or was it in motion?
Rest.
It was at rest. It wanted to stay at rest. My hammer could not change that. Now, when I took the brick away, why did the can get crushed?
Because it didn't have anything blocking it.
There was nothing to block it. The can was not enough to stop the movement of the hammer. That's Newton's first law, and that's what we're going to be working with today. Now, okay guys, so we've looked at a couple of ways to keep some different things constant. For this last experiment, let's keep acceleration constant. Now, an easy way to do this is to use the force of gravity. The force of gravity pulls all things down at the same rate. And here on Earth, that rate happens to be 9.8 meters per second squared. This means that if I drop a full water bottle, at the same time as I drop a partially somewhat empty water bottle, they're going to fall at the same time. Now let's talk about why this is the case. Let's say bottle A has twice as much mass as bottle B. That means that it will also have twice as much weight as bottle B. That means that gravity is pulling twice as much on A than it is on B. So that might bring up an idea of, well, if that's the case, how come A is not going to fall faster since gravity is pulling on it more? The answer is simple. More mass means it's also going to resist more, which means they're going to end up canceling each other out. And when I drop A and B at the same time, let's see what happens. Okay, teams, excellent job. Now I want to direct your attention to the student interface. So if you will take a look at your computers, you're going to see that I have now sent you 11 buttons at the top of your student interface. I want you to click on the one that says yoga. It's about the 5th one over. So if you will all click on that now, we are going to see a video here that Dr. Newton and Dr. Law have put together of an example of how Newton's third law occurs in everyday circumstances. And I want you to take your student lab journal, and as we are watching this video together, I want you to jot down as many examples as you can see of those action and reaction pairs that we talked about. Looks like we're going to see a big one here in just a minute, guys, so let's take a look. Oh, yep, sure enough. So there's one obvious example, but there are, of course, many other examples. I want you to discuss it with your team. Write down the examples that you saw of Newton's third law occurring.